Beneath the waves lies the deep sea, a vast alien world more mysterious than the moon. Here, life thrives in darkness and crushing pressure, evolving in ways we're only beginning to understand. Our brief visits reveal a frontier teeming with strange beauty, reminding us how much remains undiscovered. Imagine cities beneath the ocean, glowing domes, coral parks, and streets of water. Building these habitats means rethinking air, power, and food, but it's a chance to create sustainable societies in harmony with the sea. For future generations, the ocean could become home, inspiring new ways to live and protect our planet. The dream of deep-sea cities is about pioneering a bold, symbiotic future. As land grows crowded and climate change threatens coasts, the ocean offers space and resources. Underwater cities could turn rising seas into opportunity, tapping clean energy and unlocking medical breakthroughs from marine life. This vision isn't just escape, it's a leap forward, sparking innovation and hope. Welcome to the dawn of deep-sea cities. Our cities sprawl, land vanishes, and nature suffers as we run out of space. Overcrowding strains resources and well-being, pushing us to seek new frontiers. The ocean's vastness offers a release valve, a chance to build anew without repeating old mistakes. The ocean covers most of our planet, yet remains uninhabited, a continent of liquid space. Here we could harness tidal energy, farm vertically, and create closed-loop, sustainable societies. Underwater living isn't just relocation, it's reinvention, solving problems by embracing the ocean's potential. The sea is our next great opportunity, waiting to be explored. As sea levels rise and coastal cities face flooding, humanity must rethink its relationship with the ocean. Instead of retreating, imagine transforming our cities, building underwater habitats that offer safety and continuity. Deep-sea cities could become sanctuaries, protecting communities from storms and preserving culture in a changing world. The deep sea is the next great frontier, an engine for economic growth, innovation, and discovery. Building underwater cities will spark revolutions in technology, resource management, and science. From mining rare minerals to unlocking new medicines and creating unique tourism, these cities will drive prosperity and shape the future of our world. Before we can colonize Mars, we must first master extreme environments here on Earth. The deep sea is the ultimate training ground, mirroring the isolation, danger, and technical challenges of space. Every lesson learned underwater brings us closer to thriving beyond our planet. The journey into the deep is a vital stepping stone to the stars. Humanity has long dreamed of worlds beneath the waves. From Plato's Atlantis, an advanced civilization lost to the sea, to Jules Verne's visionary submarine in 20,000 Leagues Under the Sea, our imagination has transformed the ocean from a place of myth and monsters into a frontier of possibility. Science fiction and real-world innovation now work hand in hand, inspiring us to build the underwater cities once only dreamed of. Jacques-Yves Cousteau dreamed of living beneath the sea, not just visiting it. His Conshelf projects made that dream real. Habitats on the ocean floor where aquanauts lived and worked for weeks. These experiments proved humans could call the ocean home, inspiring future generations to explore and imagine life under the waves. While Jacques Cousteau pioneered underwater living, the U.S. Navy launched the Sea Lab program, testing if humans could live and work deep beneath the sea. Led by Captain George F. Bond, Sea Lab's missions pushed the limits of human endurance and technology. Astronaut Scott Carpenter became the first to be both astronaut and aquanaut. Though tragedy struck, Sea Lab proved humans could survive and work in the deep sea. After Cousteau and Sealab, dreams of underwater cities faded, but visionaries kept designing. Japan's Shimizu Corporation proposed the Ocean Spiral, a self-sustaining underwater city for 5,000 people. Other architects imagine eco-friendly ocean scrapers, underwater hotels, and futuristic habitats. These bold concepts bridge past experiments and a future where deep-sea cities may finally become reality. The greatest challenge in building a city beneath the sea is the immense, unforgiving pressure. At 300 meters deep, structures must withstand 30 atmospheres, enough to crush a submarine like a soda can. Architects use advanced materials, curved shapes, and embedded sensors to create resilient, intelligent habitats, dynamic fortresses against the ocean's relentless force. The breath of life, air and atmosphere. In a deep-sea city, air must be created and carefully balanced. Electrolysis of seawater provides oxygen, while advanced systems scrub out carbon dioxide. The city becomes a self-sustaining bubble, Earth's atmosphere, recycled and protected deep beneath the ocean. A triumph of environmental engineering. Powering the abyss. Energy from the ocean. A deep-sea city must generate its own electricity, harnessing the ocean's power. Technologies like ocean thermal energy conversion, underwater turbines, tidal generators, and floating solar farms can provide clean, reliable energy. By combining these, the city thrives as a beacon of light in the deep. The underwater harvest, a new kind of farming. Feeding thousands underwater means rethinking food. Traditional farming isn't possible here, so the city grows its own food: fish, seaweed, and vegetables in high-tech, sustainable farms. Aquaculture, kelp gardens, and hydroponics create a closed-loop ecosystem, turning the city into its own breadbasket beneath the sea. Section 5. Navigating the depths, transport and logistics. Movement within and between deep-sea cities, as well as connections to the surface world, would require a complete rethinking of transportation. The familiar landscape of roads, railways, and airports would be replaced by a three-dimensional network of underwater routes and advanced submersible vehicles. The primary mode of personal and public transport within the sprawling, multi-level city would be a fleet of compact personal submarines. These subcars would be all-electric, whisper-quiet, and equipped with sophisticated navigation systems, allowing residents to glide silently through pressurized, water-filled tunnels or across the open seafloor between different habitat domes, much like driving a car through city streets today. For longer distances and mass transit, larger submarine buses or trains would operate on fixed schedules along major underwater thoroughfares. These transport corridors could be a network of large-diameter transparent tubes, allowing passengers to enjoy stunning views of the marine world during their commute. Alternatively, they could be designated submarine highways on the ocean floor, guided by sonar beacons and automated traffic control systems to prevent collisions. These larger vessels would connect residential domes with industrial zones, research labs, and recreational areas, forming the backbone of the city's public transportation system and ensuring efficient movement of people and goods throughout the metropolis. The most critical transportation link, however, would be the connection to the surface. A permanent physical link would likely take the form of a massive, pressurized elevator system. Encased in a reinforced shaft, these elevators would ascend and descend thousands of feet, carrying passengers and cargo between the deep-sea city and a floating surface platform. This platform would act as the city's gateway to the world, complete with a spaceport for suborbital travel, a conventional port for ships, and an airport for aircraft. This Seavator would be the city's umbilical cord, a vital conduit for new residents, specialized equipment, and high-value trade goods that cannot be produced in the deep. For logistical operations and heavy-duty tasks, a fleet of autonomous underwater vehicles, or AUVs, and remotely operated vehicles, known as ROVs, would be indispensable. These robotic drones would be the city's tireless workforce. They would perform routine inspections of the city's exterior, carry out repairs, construct new modules, and transport heavy cargo between different parts of the city. This would minimize the need for humans to perform dangerous extravehicular activities in the high-pressure environment. The entire transportation and logistics network would be managed by a central AI, optimizing traffic flow, scheduling maintenance, and ensuring the safe and seamless operation of this complex three-dimensional circulatory system. Section 6. The human element, psychology and well-being. Beyond engineering, the true success of a deep-sea city depends on its people. Designing for mental well-being, social connection, and joy is essential. Panoramic windows, open communal spaces, and vibrant marine views help combat isolation. Green spaces and recreation nurture community and happiness. With thoughtful design, a deep-sea city can truly become a thriving, resilient home. Section 7. Building the foundation, construction in the deep. The very act of constructing a city on the seafloor is an engineering challenge of unprecedented scale. Traditional construction methods involving human workers are impractical and extremely dangerous in the high-pressure, dark, and cold environment of the deep sea. The entire process, from site preparation to the final assembly of habitat modules, would need to be reimagined, relying heavily on advanced robotics, automation, and modular prefabrication. The construction of a deep-sea city would be one of the largest and most complex robotic undertakings in human history, a carefully choreographed dance of machines in the abyss. The process would begin on the surface. The primary components of the city, the spherical habitat domes, the cylindrical connecting tunnels, the foundation structures, would be prefabricated in coastal shipyards. Building these massive modules on land would allow for greater precision, safety, and quality control. These modules would be built with all their internal systems, such as life support conduits and electrical wiring, already integrated into their structure. Once completed, these enormous components would be transported by specialized heavy-lift vessels to the designated construction site in the open ocean, ready for the most critical phase of the operation, the descent. Lowering these modules, which could weigh thousands of tons to the seafloor, would be a delicate and high-stakes procedure. Each module would be made buoyant and then carefully towed into position on the surface. Then, by systematically flooding ballast tanks, its descent would be controlled with pinpoint precision. Guided by support ships on the surface and autonomous drones below, the module would be slowly lowered through the water column to its exact location on the prepared foundation. This process would require incredibly calm sea conditions and sophisticated computer modeling to account for ocean currents and the immense forces at play, ensuring a soft and accurate landing on the seabed. Once on the seafloor, a fleet of autonomous construction robots would take over. These heavy-duty AUVs, resembling underwater bulldozers and cranes, would handle the final assembly. They would lock the modules into place on the foundation, connect them to each other with airtight seals, and link them to the city's central power and life support networks. Smaller, more dexterous robots would perform the more intricate tasks, such as welding connections and running diagnostic tests on the seals. Human oversight would be managed from a control center, either on a surface vessel or within an already established part of the city, with engineers directing the robotic workforce in real time. This remote, robot-driven construction method is the only feasible way to build the foundations of our future home in the deep. In the isolated, self-contained world of a deep-sea city, the concept of waste would have to be eliminated. Every byproduct, every discarded material, and every ounce of effluent would need to be seen as a valuable resource to be recovered, reprocessed, and reused. Mimicking the elegant, waste-free cycles found in natural ecosystems, the city would function as a closed-loop system, a marvel of environmental engineering where nothing is thrown away. This approach would not only be essential for the city's long-term sustainability and self-sufficiency, but would also be critical for protecting the pristine and delicate marine environment just outside its walls. Human and organic waste would be one of the most important resources to be recycled. Instead of being discharged into the ocean, all sewage would be collected and treated in an advanced bioreactor. Anaerobic digesters would break down the organic matter, producing two valuable outputs: biogas, primarily methane, which could be captured and used as a supplemental energy source, and a nutrient-rich slurry. This slurry, after being sterilized, would serve as a perfect liquid fertilizer for the city's hydroponic and aquaponic farms, providing the essential nutrients for growing fresh produce. This creates a perfect cycle, where the waste from consuming food is used to grow more food. Solid waste, such as plastics, metals, and glass, would be meticulously sorted and reprocessed. Plastics could be shredded and melted down to be used as raw material in the city's three-dimensional printers, which would be capable of fabricating everything from spare parts and tools to household goods and even new construction components. Metals would be melted down and recast, while glass would be crushed and reformed. This comprehensive recycling program would drastically reduce the need to import raw materials from the surface, enhancing the city's autonomy. Any material that could not be recycled would be super compacted and stored for eventual transport back to the surface, ensuring that no pollution leaches into the surrounding ocean. Even the water itself would be part of this relentless recycling effort. All gray water, from showers, sinks, and laundry, would be collected, filtered, and purified to drinking water standards. Advanced filtration techniques like reverse osmosis and ultraviolet sterilization would ensure that every drop of precious fresh water is used and reused as many times as possible. The only new fresh water entering the system would come from the city's desalination plant, which would process the surrounding seawater. By embracing a philosophy of total recycling, a deep-sea city would not just survive in its isolated environment. It would thrive as a model of perfect sustainability, a clean and efficient society with virtually no footprint on the world around it. Living within the deep sea would place humanity on the doorstep of Earth's last and greatest scientific frontier. Permanent underwater labs would let scientists become residents, not visitors, unlocking discoveries in marine biology, geology, and climate science. Deep-sea cities could transform our understanding of life, medicine, and the planet's future. A new era of discovery awaits. Living in the deep ocean, humanity would become true guardians of the blue frontier, protecting fragile reefs, restoring marine life, and tackling pollution firsthand. Aquanauts would transform conservation into a daily personal mission. With advanced tools, they'd clean the seafloor and recycle ocean plastic. Children would grow up with the ocean as their backyard, and their responsibility. Together, we'd become true custodians of our planet's blue heart. The technologies developed out of necessity for survival in a deep-sea city could have a revolutionary impact on how we live back on the surface. At the heart of it all, the core principle of an underwater habitat is absolute self-sufficiency and the creation of a perfect closed-loop system where nothing is wasted. The innovations in water recycling, waste management, and energy production required for such a city would provide a powerful blueprint for creating more sustainable societies on land. These habitats would become living laboratories for the circular economy, demonstrating on a small scale what is possible for the planet as a whole, and accelerating our transition away from a disposable, high-waste culture. Consider the city's water systems. To survive, a deep-sea habitat must be able to purify and reuse every single drop of water. The advanced filtration and purification technologies perfected for this purpose could be adapted for use in water-scarce regions on the surface. Imagine coastal cities in arid climates being able to efficiently recycle their wastewater to near potable quality, drastically reducing their reliance on depleting freshwater sources. The desalination technologies used to provide the city's initial water supply, powered by clean ocean energy, could also be scaled up, providing a sustainable source of fresh water for millions on land without the massive carbon footprint of current desalination plants. Similarly, the city's approach to waste as a resource would be a game changer. The systems designed to convert organic waste into energy and fertilizer and to reprocess all solid materials could serve as a model for terrestrial cities struggling with overflowing landfills and plastic pollution. If a sealed city of 5,000 people can achieve near-zero waste, it proves that it is technologically possible to do so on a larger scale. The innovations from the deep would inspire and enable surface communities to redesign their own metabolic systems, moving towards a future where our cities function less like linear drains on resources and more like self-sustaining regenerative ecosystems. Even the food production methods pioneered in the deep would offer solutions for the surface. High-yield, soil-free hydroponic and aquaponic farms can be stacked vertically, allowing for massive food production in a small physical footprint. This vertical farming technology, perfected in the controlled environment of an undersea city, could be deployed in urban centers on land, allowing cities to grow their own fresh produce locally. This would reduce transportation costs and emissions, improve food security, and free up vast tracts of agricultural land to be returned to nature, helping to restore biodiversity and create valuable carbon sinks. The rewards of underwater life would thus ripple upwards, helping to heal the very surface world we sought to relieve. The creation of deep-sea cities would not just be a scientific endeavor. It would be a monumental economic driver, sparking new industries and creating a wide array of jobs for a new generation of pioneers. The sheer scale and complexity of designing, building, and maintaining these underwater metropolises would ignite a boom in fields like materials, science, robotics, and specialized engineering. This would create high-skilled, high-paying jobs for architects, subaquatic engineers, and life support systems specialists. However, the economic benefits would extend far beyond the research and development phase, creating a diverse blue-collar economy that supports the city's daily life and operations in the deep. Once established, the city would require a large and varied workforce to keep it running. Technicians would be needed to maintain the O-Tech power plants, the electrolysis systems, and the complex network of robotic drones that serve as the city's maintenance crew. Skilled farmers would be required to operate the sophisticated aquaculture and hydroponics facilities that provide the city's food. The city's internal transport systems, from personal submarines to mass transit tunnels, would need pilots, mechanics, and traffic controllers. These are not the jobs of the distant future. They are the practical, hands-on roles that would form the backbone of a thriving deep-sea economy, offering meaningful employment to thousands. The ocean itself would become a new workplace. With a permanent base of operations on the seafloor, industries like responsible deep-sea resource extraction would become safer and more efficient. Instead of operating from a distant surface ship, human-supervised robotic mining operations could be managed from a nearby control center within the city, allowing for more precise and environmentally sensitive extraction of critical minerals. Furthermore, deep-sea salvage and repair operations for underwater cables and pipelines would become far more feasible, with expert teams able to deploy directly from a local habitat rather than a vessel hundreds of miles away, creating a hub for subsea industrial services. Finally, the tourism and hospitality sector would be a major economic engine. Underwater hotels, restaurants with panoramic ocean views, and adventure tour companies offering guided submarine excursions would create a wealth of service industry jobs. The city would need chefs, hotel managers, submersible tour guides, and dive instructors. This would create a vibrant and diverse community, ensuring that the city is not just a sterile scientific outpost, but a lively and dynamic place to live and work. The economic rewards of underwater life are multifaceted, promising not just technological progress, but the creation of a robust and self-sustaining society with opportunities for people from all walks of life. Building cities in the deep sea would transform how we see ourselves and our planet. Like explorers before us, we'd unite to overcome challenges, forging a new culture of cooperation and resilience. Living beneath the waves, we'd gain a profound appreciation for Earth and discover a more unified, hopeful version of humanity. The greatest threat to any deep-sea city is the crushing pressure of the ocean, a force that never relents. Even a tiny flaw can cause catastrophic failure. Every structure must withstand immense stress, corrosion, and unpredictable geological events. In the deep, survival depends on constant vigilance, engineering excellence, and respect for the ocean's unfathomable power. While engineers focus on protecting the body from the ocean's pressure, an equally critical challenge is protecting the mind from the psychological strain of deep-sea life. Humans evolved on the sunlit savannas of Africa, hardwired to live under an open sky with the natural rhythms of day and night. Placing them in a sealed, artificial environment deep beneath the waves for months or years at a time is an experiment with profound psychological risks. The absence of natural sunlight, the confinement of the habitat, and the constant awareness of the lethal environment just outside the walls could create a potent cocktail of stress, anxiety, and depression. The silent siege on the human psyche could be just as dangerous as the physical pressure. One of the most significant challenges is isolation. Even in a city of thousands, the community would be profoundly isolated from the rest of humanity. Communication with the surface would exist, but the physical separation would be immense. This could lead to a powerful us versus them mentality, or a collective feeling of being forgotten and alone. For individuals, the inability to simply walk outside and feel the sun or wind can be deeply unsettling over time. This condition, sometimes called breakaway phenomenon by psychologists studying isolated groups, can lead to irritability, interpersonal conflict, and a dangerous detachment from reality. Building a cohesive and mentally resilient society under these conditions will be a monumental task. The environment itself, while beautiful, is also monotonous. The view from the window would be a world of blue and black, populated by slow-moving creatures. While initially mesmerizing, this could eventually lead to sensory understimulation. To counteract this, the city's interior design must be rich, varied, and engaging, with vibrant public spaces, green parks, and diverse entertainment options. Access to high-fidelity virtual reality experiences could provide a crucial psychological escape, allowing residents to visit a forest, a beach, or a bustling surface city. Without such outlets, the risk of claustrophobia and a pervasive sense of boredom could undermine the morale and well-being of the entire population. Finally, there is the ever-present psychological weight of the danger. Every resident would know that their life depends entirely on the flawless functioning of technology. The constant low-level hum of the life support systems would be a permanent reminder of their fragile existence. This background anxiety could take a heavy toll over time, leading to sleep disturbances and other stress-related health problems. A city beneath the sea must therefore have a robust mental health infrastructure with readily available counseling and support systems. The selection of residents would also be critical, favoring individuals with proven psychological resilience, adaptability, and strong cooperative skills to withstand the silent siege on the mind. The dream of building a city beneath the waves comes with an astronomical price tag. The research and development required for new materials, life support systems, and robotic construction alone would cost billions of dollars. The construction itself, prefabricating massive modules, transporting them to the site, and assembling them on the seafloor, would be one of the most expensive engineering projects ever undertaken, likely costing hundreds of billions if not trillions of dollars. This is not a cost that a single corporation or even a single nation could easily bear. Securing the necessary funding would require an unprecedented level of global cooperation, or a private investor with unimaginably deep pockets and a long-term vision. Even if the funding were secured, the question of ownership and governance would create a labyrinth of political and legal challenges. Who owns the seafloor? According to the United Nations Convention on the Law of the Sea, the seabed beyond national jurisdiction is considered the common heritage of mankind. This means that no single nation can claim sovereignty over it. So, under what laws would a deep-sea city operate? Would it be a self-governing city-state, a corporate-run entity, or an international territory administered by a body like the UN? These questions of sovereignty, law enforcement, and regulation would have to be resolved before the first foundation is ever laid. The economic viability of such a city is also a major uncertainty. The initial proponents suggest that industries like deep-sea mining, biotechnology, and luxury tourism would make the city profitable. However, these are largely unproven markets. Deep-sea mining is fraught with environmental concerns that could lead to strict international regulations, limiting its profitability. The market for ultra-luxury underwater tourism may be small, and the revenue generated might be a drop in the ocean compared to the city's massive operational and maintenance costs. The city could become a money pit, perpetually dependent on subsidies from the surface, a spectacular achievement that is economically unsustainable in the long run. Furthermore, The strategic and military implications of deep-sea habitats would be a source of international tension. A nation or corporation that controls a deep-sea city would have a significant strategic advantage, with the ability to monitor submarine traffic, control access to resources, and potentially deploy undersea military assets undetected. Other nations might view such a settlement as a threat, leading to a new underwater arms race and a Cold War in the deep. The dream of a peaceful scientific utopia could quickly be overshadowed by geopolitical competition and conflict, turning the new frontier into a new battleground for old rivalries on the surface. Building a deep-sea city could irreversibly damage fragile marine ecosystems. Construction noise, light, and pollution threaten ancient species and disrupt natural cycles. We've explored less than 5% of our oceans. Before we build, we must understand and protect these mysterious worlds, so our next frontier doesn't become our next ecological tragedy. Imagine waking up to the gentle glow of circadian lighting, gazing out at the tranquil blue of the mid-ocean. Your commute is a serene glide in a personal submarine, passing lantern-eyed fish and giant squid. In this deep-sea city, life blends the futuristic and familiar, a thriving, sustainable community deeply connected to the ocean's mysterious realm. The journey into the deep sea, like space, begins with small, deliberate steps. Our first underwater outposts will be research stations, testing life support, construction, and the human spirit. From these, new ventures and underwater cities will rise, not to conquer the ocean, but to join it, ushering in a new chapter for humanity.